Okay, very good morning to all. Today we are going to discuss about some basics of electronics. Okay, electronics means it's a branch of engineering which deals with current conduction through a vacuum or gas or semiconductor is known as electronics. That means it is a branch of science which deals with the current conduction through any devices which are current conduction through a medium of vacuum or any medium of gas or semiconductor is known as electronics. Okay, so an electrical devices means which are working on the high current ranges, but electronic devices which are working on low current ranges. Okay, and the branch electronics which gets more importance in our present time because there are numerous applications like numerous application on electronic devices such as some functions, for example, rectification. Rectification means it is a conversion of alternating current into DC, AC to DC is called rectification. And amplification, the process of raising the strength of a weak signal is known as amplification. And for that, we are using some electronic devices and also control of signals and generation. Generation means electronic devices can convert DC power into AC power also. And at any frequency, it is possible to generate DC power to convert DC power into AC power at any frequency is possible by using oscillators. Conversion of light into electricity by using electronic devices is possible, or that is photoelectricity. The conversion of light into electricity is known as photoelectricity, and also conversion of electricity into light is also possible by using electronic devices. So there are many important devices on electronics which function as rectification, amplification, control of signals, generation, conversion of light into electricity and electricity into light. Such all are possible by using electronic devices. So now we know generally the materials are classified into three. That is, according to the material properties, they are classified into conductors, insulators, and semiconductors. So the mainly electronics, it's a branch we have already told that it is the current conduction through semiconductor. So the property of semiconductor is it lies in between. The conductivity of semiconductor material lies in between the conductivity of conductors and insulators. Conductor have high conductivity. That means the resistivity is very less. Number of free electrons in that material will be large. So if we apply a potential difference on that material, conducting material, the free electrons will flow in the direction as we applied the potential. Okay. But in semiconductors, the number of free electrons will be less. If in a pure semiconductor, it will be negligible. So at pure condition, the purest form of semiconductor will act as an insulator. By adding some impurities, we can improve the conductivity of semiconductor, and also by applying temperature. When temperature increases, it will produce number of free electrons in semiconductor material due to the increase in temperature. So by increasing temperature, the resistivity can be reduced. This resistivity of semiconductor can be reduced. So we called it as negative temperature coefficient device. But in conductor, if we increase the temperature, resistance will also increase. But semiconductors are negative temperature coefficient devices. Okay, so the property of semiconductors, I am again telling that semiconductors have the conductivity in between conductors and insulator. Insulator, you know, the resistivity is very high, it will not conduct the current through it. So the resistivity of a semiconductor, resistivity or conductivity of a semiconductor lies between the property of conductor and insulator. And also when temperature increases, the current conduction of semiconductor can also increases, or by adding any impurities to the semiconductor, we can improve the conductivity of the semiconductor. Okay, and The semiconductor. Now we are going to study about semiconductors. Okay, because most of the electronic devices are manufactured by using semiconductors. Semiconductor is a substance which has resistivity in between conductors and insulators. And now we are going to study about the bonds in semiconductor. Okay. Now, in a semiconductor, bonds are formed by sharing of valence electrons. Sharing of valence electrons means we know that the semiconductor materials, for example, silicon, germanium, the fourth group of materials are um, the semiconductor materials. That means the outermost shell, each atom have the outermost shell having four number of electrons on it. So in semiconductor bonds are formed by sharing of valence electrons, because to get in a stable condition, it will acquire four more electrons to its outermost orbit. So it can be stable. So such bonds are not called as covalent bonds. That means semiconductor which is formed by sharing of valence electron. The bonds formed by sharing of valence electrons is known as covalent bond. In the formation of a covalent bond, each atom contribute equal number of valence electrons. So equal number of valence electrons, and the contributed electrons are shared by the atoms engaged in the formation of the bond. Okay, so I share my screen. You can see that. Okay, I'm sorry, just a second. Okay, now we are going to study about semiconductors. So in this, you can see here there are three orbits for an atom. It's a atomic structure of or crystalline structure of a silicon atom. Okay, silicon atom in which the outermost orbit you can see only four electrons. Here you can see now four electrons are at the outermost orbit. So you know to become stable it needs four more electrons to the outermost orbit. So it will share the outermost electrons with a neighboring silicon atom. Okay, you can see by sharing electrons the silicon atom will attain four its own its own electrons is shared with the neighboring outermost electrons of another silicon atom. So this outermost orbit will have now 8 electrons. So the silicon atom becomes stable. So by sharing electrons of neighboring to the neighboring atom is known as covalent bond. Okay. Now here I am just comparing the substance conductors, semiconductors, and insulators and their resistivity accordingly. Okay, here also it's a germanium semiconductor material. It is making covalent bonds with the neighboring germanium atoms. Okay, covalent bonds. So it's the semiconductor material have a crystalline structure with the covalent bonds. Okay, so now we are going to study the energy band diagram of a or description of a semiconductor material. You know that here you can see in the purest form, actually there is no free electrons in the atom, but due to the room temperature itself, some covalent bonds will be broken and there will be some electrons will be detached from its atomic structure. So atomic means to the nucleus, all the outermost electrons are uh, tightly bonded or tightly attracted to the nucleus of the atom. So that atoms can detach from the attraction of nucleus by room temperature itself. Some of the electrons will detach from the attraction of nucleus from its outermost orbit. So that free electron will contribute a small current in the purest form of semiconductors. Okay, now we are going to study the energy band diagram. Here you can see in a silicon atom, it has three orbits. In the first orbit, it has two electrons. These two electrons will have one energy level. And the second orbit electrons will have a higher energy level than the first orbit. And the another orbit, the outermost cell, which is known as valence band. This outermost orbit have four electrons which have a different level of energy. So here you know that in a crystalline structure there are numerous silicon atoms are present. So in each silicon atom there are first orbit atom, numerous first orbit atoms. So these first orbit atoms will create a band of energy level that is represented here. The first band is not here. Here you can see the first band of energy level, and the second orbit electrons will have another band, another different level of energy, which is represented by this band, which is higher than the first band, and the outermost orbit will have higher energy than the second orbit, that is represented by this band. That is, here there are number of electrons for each silicon atom. There are outermost shell which have four electrons will have a band of energy. That energy is represented as this valence band in the energy band diagram. Okay, for a silicon atom, it has three bands. First band electrons, first band represents the energy level of first orbit electrons. Second band represents the energy level of orbit electrons of each silicon atom. And here, valence band represents the energy level of outermost electrons in each silicon atom. Now, when the another higher level is known as conduction band. When electron from the outermost orbit and reaches to the conduction band, then only it can contribute current flow. That means if the electrons in the outermost shell here, if outermost orbit electrons is detached from the nucleus, then only it can produce, it become free, or it can produce or contribute current through that material. Okay, so to get that energy level, so one electron in valence band, if it acquire an energy level that is 1.1 electron volt is the energy gap of silicon electrons to reach the conduction band. Conduction band energy level is higher than the valence band energy, so it have to acquire more energy to become in the conduction band. So ഒരു ഇലക്ട്രോൺ വാലൻസ് ബാൻഡിലുള്ള ഒരു ഇലക്ട്രോണിന് കണ്ടക്ഷൻ ബാൻഡിലോട്ട് എത്തണമെങ്കിൽ ഒരു കുറച്ച് എനർജിയും കൂടെ അത് അക്വയർ ചെയ്യണം. So in a silicon it is 1.1 electron volt, in germanium it is 0.7 electron volt. So electrons in the valence band, if it acquires some energy, higher energy, it can reach at the conduction band. So, and also it can contribute current, or conductivity can be increased by these free electrons. So, when atoms bond together form a solid. Here you can see when atoms bond together, it is a solid. The orbit of an electron is influenced not only by charges on its own atom, by the nuclei and electrons of every atom in the solid. There are millions of electrons belong to the first orbit atom in the solid. Each of them has different energy. Therefore, there are millions of first orbit electrons. You can see there are millions of first orbit electrons for each silicon atom, and it is closely spaced energy levels differing very slightly in the energy which form a cluster of band. Similarly, the second orbit and higher orbit electrons also forms different bands, that is represented here. Okay, so this figure represents energy band diagram of a solid silicon. Here it is a solid germanium. Okay, an additional band called conduction band is shown above the valence band. Okay, so all the three lower bands, including the valence band, are shown completely filled. Okay, here you can see first band is filled, second band is filled, third band, that is valence band, is filled. A band is filled means all the permissible energy levels in the band are occupied by electrons. Is occupied by electrons. An electron in a completely filled band cannot contribute cannot contribute to electric current. Actually, that is closely attached to the nucleus, so it cannot contribute electric current in these bands. First band, second band, third band, electrons at atmospheric temperature normally adinu electronic current contribute cheyan pattilla because it cannot move from the attraction of its own nucleus. So the conduction band represents the next larger group of permissible energy level. So there is an energy gap Eg. This energy gap is known as forbidden energy gap, e.g. between the valence band and conduction band. An electron can be lifted from the valence band to the conduction band, okay, by adding some energy to the solid. This energy must be more than the energy gap Eg. That is, this energy gap. If the electron in conduction band acquire energy more than 1.1 electron, then it reach here. That is conduction band. The energy must be more than the energy gap. This gap is called forbidden energy gap. For conductors, this will be in overlapped condition. That means an electron in the valence band can move to the conduction band in a pure conductors. But in semiconductor, there will be some distance in between the energy level of valence band and conduction band. Okay. This gap is called forbidden energy gap. For silicon, it is 1.1. For germanium, it is 0.7 electron volt. Note that, which is important term. Okay. And the next one is, okay. Now we are going to study about PN junction. Before that, I am going to explain about there are two types of semiconductors. Okay. Mainly, which is classified as intrinsic semiconductor and extrinsic semiconductor. Okay, intrinsic semiconductor means it is a semiconductor in an extremely pure form is known as intrinsic semiconductor. ഏറ്റവും purest ഫോമിലുള്ള സെമികണ്ടക്ടറിനെയാണ് നമ്മൾ intrinsic semiconductor എന്ന് പറയുന്നത്. An intrinsic semiconductor has only 4 electrons in the outermost of its atom. And to fill the valence shell, each atom requires 4 more electrons. 4 more electrons. Okay. So you have seen that it needs 4 more electrons to make covalent bond with the outermost electrons. So this is done by sharing 1 electron from each of the neighboring atoms. The atom align themselves in a uniform 3-dimensional pattern so that it has a crystalline structure. A covalent bond consists of 2 electrons. In a covalent bond, you can see here, we have already seen here. One covalent bond consists of 2 electrons which are sharing with the 2 atoms. Okay. Both the electrons are shared by the 2 atoms. And at absolute zero, all the valence electrons are tightly bound to the parent atom. The semiconductor therefore behaves as a perfect insulator at absolute zero. But at room temperature, some covalent bonds are broken. As room temperature may be sufficient for the valence electron to move away from the attraction or influence of its own nucleus. When an electron breaks a covalent bond and moves away, a vacancy is created in the broken covalent bond. Or electron നമ്മുടെ ന്യൂക്ലിയസിന്റെ അട്രാക്ഷനിൽ നിന്ന് ഡിറ്റാച്ച് ചെയ്ത് പോവുകയാണെങ്കിൽ ആ പൊസിഷനിൽ ഒരു ഹോൾ ക്രിയേറ്റ് ചെയ്യും, ഒരു വേക്കൻസി ക്രിയേറ്റ് ചെയ്യും. ദിസ് വേക്കൻസി ഈസ് കോൾഡ് ഹോൾ. Free electrons and holes are always generated in pairs. That means ഒരു ഇലക്ട്രോൺ ഡിറ്റാച്ച് ചെയ്യുമ്പോൾ ഒരു ഫ്രീ ഇലക്ട്രോൺ പ്രൊഡ്യൂസ് ചെയ്യും, and the position which detached, that creates a hole which have positive charge. Therefore, the concentration of free electrons and holes will always be equal in an intrinsic semiconductor. This type of generation of free electrons hole pairs is referred to as thermal generation. Okay. atmospheric temperature കാരണം detach ചെയ്യുന്നത് free electrons produce ചെയ്യുന്നതിനെയാണ് നമ്മൾ thermal generation എന്ന് പറയുന്നത്. So, and we have already told there are intrinsic and extrinsic semiconductor. Extrinsic semiconductor means if you are adding an impurity to the semiconductor. Okay, so practically all semiconductor devices are made of a semiconductor material. So we need to improve the conductivity of that semiconductor material. So to improve the conductivity, certain specified types of impurities have been added. The process of deliberately adding impurities to a semiconductor material is called doping. So നമ്മളൊരു ഡെലിബറേറ്റ്ലി ഒരു ഇമ്പ്യൂരിറ്റി അതിനകത്തോട്ട് ആഡ് ചെയ്യുവാണെങ്കിൽ അതിനെയാണ് നമ്മൾ ഡോപ്പിംഗ് എന്ന് പറയുന്നത്. പ്രോസസ് ഓഫ് ആഡിങ് ഇമ്പ്യൂരിറ്റി ടു ദ semiconductor is known as doping. A doped semiconductor is called extrinsic semiconductor. Depending upon the type of impurity added to the extrinsic semiconductor are classified into two. N-type and P-type semiconductors are there. N-type, first I am discussing about N-type semiconductors. When the small amount of pentavalent impurity means the atoms which have in the outermost shell, it has 5 electrons. The semiconductors which have 4 electrons in the outermost shell, but in pentavalent impurities have 5 electrons in the semiconductor 4 electrons. Pentavalent impurity in outermost shell it has 5 electrons. So okay, when a small amount of pentavalent impurity is added to a pure semiconductor, it is known as N-type semiconductor. For example, phosphorus, arsenic, all are pentavalent impurities, which is added to a silicon atom. Here it is germanium atom. Okay, when an arsenic is added to a germanium atom, you can see which creates 4 bonds to the arsenic atom with the neighboring germanium atom. Okay, so this forms covalent bond with the 4 neighboring silicon or germanium atom. The 5th electron you can see here, which is that electron is very loosely bounded with the nucleus of that arsenic atom. Okay, so it very little energy to free itself from the attractive force of its nucleus. So it need only small energy to detach that free electron from this nucleus of arsenic. If free electron ഈ ആഴ്സനിക്കുമായുള്ള അട്രാക്ഷന് ഡിറ്റാച്ച് ചെയ്യാൻ ചെറിയൊരു റൂം ടെമ്പറേച്ചറിന്റെ ആവശ്യമേ ഉള്ളൂ. So all such electrons become free at the room temperature itself. So it can donate. So this type of impurity can donate 1 electron, and this type of impurity is called donor impurity. The donated electrons are called excess electrons. So arsenic pentavalent impurities are known as donor impurity, and the donated electrons are called excess electrons. These will also some electron hole pairs. Some electron hole pairs can be also formed here. Okay, which is generated because of breaking of covalent bond. We know that at room temperature itself, some covalent bonds are broken and there will be a free electron and a hole pair. So the free electrons can reach that positively charged holes and it recombine with that holes. That is told. That means a free electron നമ്മുടെ already അതിനകത്ത് സിലിക്കൺ or ജർമാനിയം ആറ്റത്തിനകത്തുള്ള ഹോൾസുമായി റീകമ്പൈൻ ചെയ്യാൻ പറ്റും. എന്നാലും അറ്റ് റൂം ടെമ്പറേച്ചറിൽ കുറച്ച് ഹോൾസേ ഉണ്ടായിരിക്കുള്ളൂ. സോ ദർ വിൽ ബി ഇലക്ട്രോൺ ഹോൾ പെയേഴ്സ് ഉണ്ടാകുമെങ്കിലും അത് വെരി സ്മോൾ നമ്പർ ആയിരിക്കും ആസ് കമ്പയർഡ് ടു ദ നമ്പർ ഓഫ് ഫ്രീ ഇലക്ട്രോൺസ്. നമ്മൾ ആഡ് ചെയ്ത ഇമ്പ്യൂരിറ്റീസ് പ്രൊഡ്യൂസ് ചെയ്യുന്ന ഫ്രീ ഇലക്ട്രോൺസിനേക്കാളും വളരെ കുറച്ച് ആസ് കമ്പയർഡ് ടു ദാറ്റ് നമ്പർ ഇറ്റ് വിൽ ബി വെരി ലെസ് ദാറ്റ് holes produced by room temperature itself by breaking covalent bond. Okay, so when we added an impurity to the atom, it produces free electrons, but in the at room temperature there will be some covalent bonds are broken and there will be a hole. This free electron will move to that hole and recombine with that hole, but then also there will be numerous of free electrons in the extrinsic semiconductor. So the number of thermally generated electron hole pairs will be very small as compared to the number of free electrons due to impurity atoms. As the free electrons increases, their combination with holes also increases. The net concentration of electrons is more than that of holes. So in extrinsic semiconductor, number of free electrons is more than that of holes. So it becomes a negative type semiconductor. Okay, negative type because electrons have negative charge. Number of electrons is higher in the n-type material. So it is called as n-type semiconductor. So in n-type semiconductor, it has electrons as the majority carriers and holes as the minority carriers. Okay. So here we already told us the semiconductor materials are of two type, intrinsic and extrinsic, and the extrinsic semiconductors are of two type, n type and p type. So now we are going to discuss about the p type semiconductors. If we added a trivalent impurity to the intrinsic semiconductor, in n-type material we added pentavalent impurity. That means it consists of 5 electrons at the outermost shell. But in p-type material we are adding trivalent impurity. That means at the outermost shell that atoms with trivalent impurity will have only 3 electrons. So if we added a trivalent impurity to the intrinsic semiconductor, the result will be a p-type semiconductor. Just consider this. Yeah, just consider a germanium intrinsic semiconductor. Into that we are adding gallium or boron or trivalent impurities. Here we are adding a gallium trivalent impurity to the germanium crystal. Okay. So it has 3 valence electrons. That 3 valence electrons will combine with the neighboring germanium atom, and these electrons form covalent bond with these neighboring atom. Okay, there is a but here there is a deficiency of one electron, an electron around the boron atom. Then here this deficiency that creates a hole. That means there is a missing of electron. Then an electron n. Then an electron form the adjacent covalent bond jumps to fill the vacancy. That means an electron in the adjacent covalent bond will jumps to this vacancy because we know that the hole will have positive charge. So that neighboring electron will jump to this positively charged hole and it creates a hole here and that hole moves to here. Okay. അതായത് നമ്മൾ ഒരു ട്രൈവാലന്റ് ഇമ്പ്യൂരിറ്റി ആഡ് ചെയ്ത് കഴിയുമ്പോൾ 3 ഔട്ടർ മോസ്റ്റ് ഇലക്ട്രോൺസും കോവാലന്റ് ബോണ്ട് ക്രിയേറ്റ് ചെയ്യും. പക്ഷെ വീണ്ടും ഒരു കോവാലന്റ് ബോണ്ട് കൂടെ ക്രിയേറ്റ് ചെയ്യാനുള്ള ഒരു ഇലക്ട്രോൺ അവിടെ മിസ്സിംഗ് ആയിരിക്കും. ഈ മിസ്സിംഗ് വേക്കൻസി എന്ന് പറയുന്നത് ഹോൾ ആണ്. ദാറ്റ് ഹോൾ എന്ന് പറയുന്നത് ഒരു പോസിറ്റീവ്ലി ചാർജ്ഡ് പോർഷൻ ആണ്. സോ നൈബറിംഗ് ഇലക്ട്രോൺ വിൽ attract to this hole and it will recombine to this hole, and here this electron detached from here to here. So here a hole will be produced. So this gallium becomes negative ion because it receive one electron from the neighboring atom. So this gallium or boron accepts one electron from the crystal. Therefore, this type of impurity is called acceptor impurity. In n-type, that is n-type donor impurity because it donating one free electron. But here, trivalent impurity is accepting one electron from the neighboring atom. So it is acceptor impurity. P-type semiconductor has holes as the majority carrier. So holes ആണ് ഇവിടെ മൂവ് ചെയ്യുന്നത്. സോ മെജോറിറ്റി കാരിയേഴ്സ് എന്ന് പറയുന്നത് ഹോൾസ് ആയിരിക്കും പി ടൈപ്പിൽ. ആൻഡ് ഇലക്ട്രോൺസ് ആർ ദ മൈനോറിറ്റി കാരിയേഴ്സ് ബിക്കോസ് കുറച്ച് റൂം ടെമ്പറേച്ചർ കാരണം ഡിറ്റാച്ച് ചെയ്ത ഫ്രീ ഇലക്ട്രോൺസ് മാത്രമേ അതിനകത്ത് ഉണ്ടാവുള്ളൂ. സോ അതൊരു മൈനോറിറ്റി കാരിയേഴ്സ് ആസ് കമ്പയർഡ് ടു ദാറ്റ് ഫ്രീ ഇലക്ട്രോൺസ് നമ്പർ ഓഫ് ഹോൾസ് ഇസ് more in the p-type material. So p-type material is is a acceptor impurity. It has acceptor impurity in N type. We are using donor impurity. Okay. When we apply a voltage, a cell of voltage across this cell, that free electrons or holes will move as the polarity of the cell. Here it is representing as such. If it is a positive terminal here, the holes in the p type will move towards the negative terminal. So the current conduction will be like this. Okay. Now we are going to discuss about PN junction. When a p-type material or semiconductor is suitably joined to a n-type semiconductor, then the this contact surface is known as PN junction. This contact surface is known as PN junction. Here the figure shows PN junction just immediately after it is formed. നമ്മൾ ജസ്റ്റ് ഇതിനെ അങ്ങോട്ട് ജോയിൻ ചെയ്യുമ്പോൾ ഉള്ള ഒരു ഫോമാണ് ഇവിടെ കാണിക്കുന്നത്. It is a single crystal with a p-type semiconductor and an p-type semiconductor in the left and the n-type in the right. Okay. The p region has, we know that in the p region the majority carriers are holes and the negatively charged impurity because it accepts the electrons from the neighboring atoms. So they are negatively charged impurity atoms, but the majority carriers are holes. Okay, the n region has free electrons and the positively charged impurity atom because that atom donates one electron, so it is positively charged impurity atom. At the junction, there is a tendency for the free electrons to diffuse over this. At this junction, there is a tendency of free electrons to diffuse over to the p side and holes to the n side. ഹോൾസിന് ഇങ്ങോട്ട് വരാനും ഇലക്ട്രോൺസിന് അങ്ങോട്ട് പോകാനുള്ള ഒരു ടെൻഡൻസി ഉണ്ടായിരിക്കും. ദിസ് പ്രോസസ് ഇസ് നോൺ ആസ് ഡിഫ്യൂഷൻ. രണ്ടിനും ഡിഫ്യൂസ് ചെയ്യാനുള്ള ഒരു ടെൻഡൻസി ഉണ്ടാവും, അതിന് നമ്മൾ പറയുന്നതാണ് ഡിഫ്യൂഷൻ. The diffusion of holes and free electrons across the junction occurs for a short time because just diffusion ഉണ്ടാകുമ്പോൾ എന്താ സംഭവിക്കുക? After a few recombination, when electron reaches at a hole, it recombine with that holes. Few electron hole recombination. The electrons in the immediate neighborhood of the junction has a restraining force. ഇവിടെ ഇത് ഇങ്ങോട്ട് join ചെയ്ത് കഴിഞ്ഞാൽ it become positive. Then വീണ്ടും ഇങ്ങോട്ട് വരാനുള്ള ഒരു ടെൻഡൻസി ഉണ്ടാവില്ല because a few combination, after the few recombination occurs, what happened? The immediate neighborhood of the junction have a restraining force set up automatically. ഒരു restraining force set up ചെയ്യും. This force is called a barrier. അതായത് നമ്മൾ once ഒരു recombination ഉണ്ടായി കഴിഞ്ഞാൽ അവിടെ ഒരു barrier produce ചെയ്യും. Okay, barrier. Further diffusion of holes and electrons from one side to other is stopped. ഒരു സൈഡിൽ നിന്ന് ഇലക്ട്രോൺസിന് ഇങ്ങോട്ട് വരാൻ കഴിയില്ല because അവിടെ ഒരു ബാരിയർ ക്രിയേറ്റ് ചെയ്യും. Okay, outside this barrier on each side of the junction the material is still neutral. Only inside the barrier there is positive charge on the n side and negative charge on the p side. This region is called depletion region. അതായത് നമ്മൾ ഇവിടെ ഒരു ഇലക്ട്രോൺ ഇങ്ങോട്ട് മൂവ് ചെയ്ത് ഇതുമായി ജോയിൻ ചെയ്ത് കഴിഞ്ഞാൽ അത് ന്യൂട്രലൈസ് ചെയ്യും. പക്ഷെ ഇവിടെ പോസിറ്റീവ് അയോണും നെഗറ്റീവ് അയോണും അവിടെ റീറ്റെയിൻ ചെയ്യും. സോ ദ അനദർ ഇലക്ട്രോൺ കംസ് ഹിയർ ഇങ്ങോട്ട് വരാൻ ശ്രമിക്കും. അതേപോലെ ഈ ഹോള് ഇത് ഇങ്ങോട്ട് വരാനും ശ്രമിക്കും. ഇങ്ങോട്ട് വരുന്ന ഹോളിന് ഇവിടെ പോസിറ്റീവ് ചാർജ് ഇതിനെ റിപ്പൽ ചെയ്യും. ഇങ്ങോട്ട് വരുന്ന ഇലക്ട്രോൺസിന് ഈ നെഗറ്റീവ് ചാർജ് റിപ്പൽ ചെയ്യും. സോ അതായത് ഒരു ബാരിയർ ഇവിടെ ഒരു റിസ്ട്രെയിനിങ് ഫോഴ്സ് ഇവിടെ ക്രിയേറ്റ് ചെയ്യും. അപ്പൊ അനദർ റീകോമ്പിനേഷൻ പോസിബിൾ ആവാതെ വരും. ആ ഒരു പോർഷനെയാണ്, അതായത് ജസ്റ്റ് ഇമ്മീഡിയറ്റ്ലി ജോയിൻ ചെയ്ത സമയത്ത് ഒരു റീകോമ്പിനേഷൻ നടന്നു കഴിഞ്ഞാൽ പ്രൊഡ്യൂസ് ചെയ്യുന്നതിനെയാണ് നമ്മൾ ഒരു റീജിയനാണ് ബാരിയർ എന്ന് പറയുന്നത്. ആൻഡ് ലെയർ, ഈ ഒരു ലെയറിൽ ആ ഒരു ബാരിയറിൽ ഫ്രീ ഇലക്ട്രോൺസും ചാർജസും അവിടെ ഡിപ്ലീറ്റ് ചെയ്തു പോയി, അതായത് നമ്മൾ റീകമ്പൈൻ ചെയ്തു പോയി. അതുകൊണ്ട് ആ ഒരു ലെയറിന് നമ്മൾ പറയുന്ന പേരാണ് or that region is called depletion layer. It is called so because the mobile charge carriers here, mobile charge carriers are holes. Here it is free electrons. But in the barrier, within the barrier, there is no free electrons or holes. So because it become recombined. So this is called a depletion layer. And when we apply a voltage, potential difference across the PN junction, it can be applied in two ways, either in this way or in this way. Either if we apply positive terminal to the P-type region and negative terminal to the N-type region, or which is known as forward biasing. Or also we can apply like this in the reverse order, negative terminal to the P-type and positive terminal to the N-type, and that type of connection is known as reverse biasing. Okay, now we are going studying about forward biasing and reverse biasing. Okay, in forward biasing, what will happen when we apply a voltage in a forward biased manner? That is, positive terminal of the battery is connected to P-type material, negative terminal of the battery is connected to N-type material. Okay, when an external voltage is applied to this junction, it will become forward biasing. Okay, the junction, when we apply like this, the junction will offers very low resistance called forward resistance. Okay, when we apply like this, it will produce a very low resistance at the junction to current flow. So current flow in the circuit due to the establishment of low resistance path. The magnitude of current depends upon the applied ഫോർവേഡ് വോൾട്ടേജ്. നമ്മൾ ഈ ഫോർവേഡ് വോൾട്ടേജ് ഇൻക്രീസ് ചെയ്യുവാണെങ്കിൽ ഈ ഒരു ബാരിയർ അതിനെ എലിമിനേറ്റ് ചെയ്ത് പോയിട്ട് ഒരു ലോ റെസിസ്റ്റൻസ് പാത്ത് പ്രൊവൈഡ് ചെയ്യും. When we apply a voltage across this junction, it will produce a low resistance path to flow of current. But when we apply the voltage or when we connect a battery like this, that means negative terminal to the positive type and positive terminal to the N type, what will happen? It is called reverse biased. To apply reverse bias, we have to connect like this, and the potential barrier will increase because negative terminal will attract the holes to here and the electrons to here. So it will be depleted from the junction. That means here the thickness of barrier will increases. So no current flows in the circuit. Neither PN junction there is no current flow through it. So to establish the high resistance, because it established high resistance at here. So this condition is known as reverse biasing. Okay. And this PN junction is known as diode, PN junction diode. Now we are going to study about the volt ampere characteristics of a PN junction. So PN junction is known as a semiconductor diode. Semiconductor diode, the symbol of diode is like this, and that this terminal is known as anode, and a bar here which is known as cathode. Okay. It permits flow of current only in one direction. We know that if it is at forward biased condition, then only a current flow will occur. If it is at reversed biased condition, a current flow will not occur within the junction. Okay. So with this property, we are going to study the VI characteristics of a PN junction. Okay. Here this is the figure shows the circuit for obtaining VI characteristics of a diode. The P region, here you can see the PN junction diode. The P region of the diode is called anode. N region of the diode is called cathode. In the circuit, a DC battery is connected to the diode. ഒരു ഡി സി ബാറ്ററി ഇവിടെ കണക്ട് ചെയ്തിട്ടുണ്ട് ടു ദ ഡയോഡ്. എങ്ങനെയാണ് നമ്മൾ കണക്ട് ചെയ്തിരിക്കുന്നത്? The diode is in forward biased condition, positive to P type, negative to N type. So since the current flows through the, we know that in forward biased condition, current will flows through the PN junction at a low resistance. It provides a low resistance path through the PN junction. So as to limit the current, we are using a resistor here. Okay, resistor R is connected to limit the current. The diode current is very small for a first few increase in voltage. Here in the characteristics, it is volt ampere characteristics. Here we are applying a voltage through a variable rheostat and a current limiting resistor is placed here. Voltmeter to measure the voltage and a milliammeter is connected for measuring the current flow through the diode. So when we apply a variable voltage from the 0 to a particular value, first initially the current will increases very small increase, and it is very small for the few seconds. Then after some time or after some value, a particular value, it increases linearly. The diode does not conduct well until the external voltage overcome the barrier potential of PN junction diode. We know that there is a barrier within the PN junction. If the voltage increases up to that potential, the current flow through this junction is very low. When we increase the value of voltage above the potential barrier, then it starts conducting. Okay, even a small in after that, when it overcome the potential barrier, a very small increase in voltage will produce a large increase in the current, and this particular value, that is the potential barrier potential, when it overcomes that barrier potential, then only it starts conducting. So this particular voltage that the diode starts conducting is known as knee voltage or cut-in voltage or barrier voltage. Knee voltage, cut-in voltage or barrier voltage. For a silicon diode, it is approximately zero point 0.7 volt. For a knee voltage is 0.7 volt for a silicon, and whereas for it is germanium, it is about zero point 0.3 volt. Okay. So this is the forward biased characteristics of a PN junction diode. When we apply a voltage from 0 to a particular value, the very small increase in current will occur up to a particular value. When the voltage overcomes the potential barrier, then the diode starts conducting. Okay. So to obtain the reverse bias characteristics, what we have to do? We have to reverse the connection of battery. Okay. Then also, we have to replace this ammeter, milliammeter by a microammeter, because there is only small leakage current will flow through this circuit on the reverse biased condition. Okay. And also if it is a germanium, only nano ampere current will flow through it. If it is silicon, then only milliampere or microampere, sorry, not milli, microampere current will be there on reverse biased condition. Okay. It is now if we apply a voltage, reverse voltage across the diode, the characteristics will be like this. Okay, the reverse bias is made too high. When we apply a reverse biased voltage in a small value, the characteristics will be, there will be a slight current through it because due to leakage current due to minority carriers. There will be some minority carriers, so it will produce a leakage current through it, that is represented by this region. But after, if we increase the reverse biased voltage at a too high value, more than 15 ഒക്കെ നമ്മൾ increase ചെയ്യുവാണെങ്കിൽ, what will happen? The PN junction, the current at the PN junction increases rapidly. The voltage at which this phenomenon occurs is known as breakdown voltage. At a particular, after the particular voltage, a breakdown will occur. So that voltage is known as breakdown voltage. At this voltage, crystalline structure of the diode will break down. There are two processes which can cause junction breakdown. ഈ junction breakdown ഉണ്ടാകാനുള്ള two processes ഉണ്ട്. It may be due to Zener breakdown or due to avalanche breakdown. So in a particular diode, the breakdown occurs due to two reasons, either by Zener breakdown or by avalanche breakdown. So when a reverse bias increases, when a voltage across it increases, what happens? The electric field at the junction also, this electric field at this junction also increases. High electric field causes covalent bond to break. When we increase the voltage across this PN junction, electric field will increases. High electric field will produce across this PN junction. but it will not conduct because potential thickness of potential barrier will increases. But at this condition, when electric field increases, covalent bond starts to break up. Thus, a large number of carriers are generated. This causes a large current to flow. Okay, this mechanism is known as Zener breakdown. When we apply a reverse voltage across a PN junction, the electric field across PN junction increases. That will cause breakdown of covalent bonds on it. Covalent bonds break ചെയ്യുമ്പോൾ എന്ത് സംഭവിക്കും? Free electrons produce ചെയ്യും. So this large current, it will be the reason for producing a large current across it. That is Zener breakdown. Any next one, other one reason is avalanche breakdown. It is due to when a reverse current applied across it, it will increase the velocity of minority carriers. We know that there is some minority carriers are free on that PN junction. So when the velocity of minority carriers increases, what happens? This high energy carriers breaks the covalent bond. That high energy carrier will move through this junction and it breaks the covalent bond within the atomic structure. That free electron move randomly. Free electrons or holes, minority carriers, it may be holes or electrons. ആ minority carriers ന്റെ velocity increase ചെയ്യും. നമ്മളൊരു റിവേഴ്സ് വോൾട്ടേജ് അപ്ലൈ ചെയ്യുമ്പോൾ ഫ്രീ ആയിട്ട് നടക്കുന്ന അതിനകത്തിരിക്കുന്ന ഇലക്ട്രോൺസിന്റെയോ ഹോൾസിന്റെയോ വെലോസിറ്റി ഇൻക്രീസ് ചെയ്യും. വെലോസിറ്റി ഇൻക്രീസ് ചെയ്യുമ്പോൾ എന്ത് സംഭവിക്കും? അത് റാൻഡം ആയിട്ട് ആറ്റോമിക് സ്ട്രക്ചറിൽ മൂവ് ചെയ്യും. റാൻഡം ആയി പോയിട്ട് അടുത്തിരിക്കുന്ന നൈബറിംഗ് കോവാലന്റ് ബോണ്ടിൽ ഹിറ്റ് ചെയ്യും and that will get higher energy and it will breaks the covalent bond and produce a free electron at the and this covalent bond breakage will produce a free electron and that free electron will acquire a high energy due to this electric field. അപ്പോൾ റിലീസ് ആയി വന്ന ഇലക്ട്രോൺസ് വീണ്ടും ഒരു ഹയർ എനർജി അക്വയർ ചെയ്യും and that free electrons will move randomly within the structure and hit with another covalent bond and which produce another breakage of covalent bond. So it become a chain reaction. Again, these generated carriers are accelerated by that electric field. They break more covalent bonds during their travel. So a chain reaction is produced due to this high velocity. So a large number of carriers will be produced. This gives rise to a high reverse current. This mechanism of breakdown, so it produces a breakdown. This mechanism of breakdown is called avalanche breakdown. So there are two breakdown mechanisms, Zener breakdown mechanism and avalanche breakdown mechanism. Zener breakdown എന്ന് വെച്ചാൽ നമ്മളൊരു റിവേഴ്സ് വോൾട്ടേജ് അപ്ലൈ ചെയ്യുമ്പോൾ അവിടെയുള്ള ഇലക്ട്രിക് ഫീൽഡ് ഇൻക്രീസ് ചെയ്യും. പി എൻ ജംഗ്ഷൻ അക്രോസ് ഉള്ള ഇലക്ട്രിക് ഫീൽഡ് ഇൻക്രീസ് ചെയ്യും. ഇലക്ട്രിക് ഫീൽഡ് ഇൻക്രീസ് ചെയ്യുന്ന കാരണം കോവാലന്റ് ബോണ്ട് ബ്രേക്ക് ചെയ്യും. അപ്പോൾ ഫ്രീ ഇലക്ട്രോൺസ് കൂടുതൽ പ്രൊഡ്യൂസ് ചെയ്യും. ഹൈ റിവേഴ്സ് കറണ്ട് പ്രൊഡ്യൂസ് ചെയ്ത് അതിന്റെ ഫിസിക്കൽ ക്രിസ്റ്റലൈൻ സ്ട്രക്ചറിനെ ഡിസ്ട്രോയ് ചെയ്യും. അങ്ങനെ ഉണ്ടാകുന്ന ബ്രേക്ക് ഡൗണിനെയാണ് സെനർ ബ്രേക്ക് ഡൗൺ എന്ന് പറയുന്നത്. അതുപോലെ അവലാഞ്ചി ബ്രേക്ക് ഡൗൺ എന്ന് പറഞ്ഞാൽ നമ്മളൊരു റിവേഴ്സ് വോൾട്ടേജ് അപ്ലൈ ചെയ്യുമ്പോൾ അതിനകത്ത് ഓരോ മൈനോറിറ്റി കാരിയേഴ്സിന്റെ വെലോസിറ്റി ഇൻക്രീസ് ചെയ്യും. ഈ മൈനോറിറ്റി കാരിയേഴ്സ് ആ ഒരു ക്രിസ്റ്റലൈൻ സ്ട്രക്ചറിൽ റാൻഡം ആയിട്ട് മൂവ് ചെയ്തിട്ട് അതിലുള്ള കോവാലന്റ് ബോൺസിൽ പോയി ഹിറ്റ് ചെയ്ത് ആ കോവാലന്റ് ബോണ്ടിനെ ബ്രേക്ക് ചെയ്യും. കോവാലന്റ് ബോണ്ട് ബ്രേക്ക് ചെയ്യുമ്പോൾ ഫ്രീ ഇലക്ട്രോൺസും ഹോൾസും പ്രൊഡ്യൂസ് ചെയ്യും. വീണ്ടും പ്രൊഡ്യൂസ് ചെയ്യുന്ന ഈ ഫ്രീ ഇലക്ട്രോൺസിന് ആ ഹൈ ഇലക്ട്രിക് ഫീൽഡ് കാരണം ഒരു എനർജി കിട്ടും. ആ എനർജി ഒരു ഹയർ എനർജി ലെവൽ കിട്ടുമ്പോൾ എന്ത് ചെയ്യും? ആ പ്രൊഡ്യൂസ് ചെയ്ത ഇലക്ട്രോൺസ് വീണ്ടും പുതിയ കോവാലന്റ് ബോൺസിനെ ബ്രേക്ക് ചെയ്യും. അങ്ങനെ അതൊരു ചെയിൻ റിയാക്ഷൻ പോലെ മോർ ആൻഡ് മോർ ഫ്രീ ഇലക്ട്രോൺസിനെ പ്രൊഡ്യൂസ് ചെയ്യുകയും ഒരു ഹൈ കറന്റ് ഫ്ലോ ഉണ്ടാവാൻ കാരണമാവുകയും ചെയ്യും. That reason or that process is known as avalanche breakdown. Okay. Then this is a semiconductor diode. ഒരു ഐഡിയൽ ഡയോഡ് എന്ന് പറയുന്നത് എന്തായിരിക്കും? An ideal diode means it conducts only in one direction. ഒരു ഫോർവേഡ് ബയസ്ഡ് കണ്ടീഷനിൽ മാത്രമേ കണ്ടക്ട് ചെയ്യുള്ളൂ. An ideal diode which acts as an automatic switch because it conducts only in one direction. If the direction of current changes, it will cut off the current flow. So it acts as a switch. Switch എന്ന് പറയുമ്പോൾ at forward biased condition it acts as a closed switch and at reverse biased condition it acts as an open switch. Okay. So these are the Okay. Today I'm stopping this topic on this diode. Okay, thank you.